Hello and welcome to another episode of the Omics Cast. In today's episode, I'm going to describe to you how to build a diagnostics NGS lab. A reminder that you can follow me on Twitter if you want, twitter.com/albertvilella. You can also contact me via LinkedIn. I'll be happy to answer any questions you have. And this slide deck is available upon request. So today I'm going to talk about how to build a diagnostics NGS lab. What are the basic steps and components to build a high throughput diagnostics NGS lab? And I'm going to base it on cfDNA samples, although most of what I'm going to be explaining in the slide deck would also be valid for other type of samples. I'll describe how to process plasma tubes through a high throughput vending machine style freezer, how to record the sample receipt through a freezer manager software, how to extract the DNA from plasma using a liquid handler, how to then take that DNA and do NGS Library Prep by a liquid handler. Once you got the library prep ready, how to submit your sequencing runs for NGS. Once you get the data from your sequencing runs, how to do the bioinformatic analysis on the cloud to get primary results, and then take all those single sample file results of the primary analysis and do a multi-sample machine learning on the cloud. So at the end of this hypothetical piece of work, setting this up, you would have a diagnostic NGS lab ready with a classifier that would classify, for example, samples as healthy or having a disease. So starting with plasma sample receipt, I'm going to show here a video you can find on YouTube. All of this material you can find on YouTube that shows a vending machine style type freezer, in this case a -80, that allows you to store all these tubes you're going to be receiving from either patients or from vendors in your discovery process, and how to store them and access them at scale. And importantly, the machine has this tray of certain number of tubes on a certain configuration that you can feed tubes in, and then when you want to get tubes out, you just give a list to the machine, pretty much as a vending machine. You say, I want this chocolate bar, or I want this drink. The same, you give a list to the machine and says, out of the thousands or hundreds of thousands of tubes that the machine has stored, please give me exactly these 96 tubes that I now want. You give it an empty rack and the machine will give you the tubes. And now the way these work in this particular provider is that it's got these cylinders that store all the material, and all the tubes are moved around in this big machine that stores them. So all this is based on being able to scanning barcodes, and it's usually two-dimensional barcodes that are scanned in. And then the tube goes in, it goes into this carousel, and then the carousel distributes them into these cylinders for later use. And then when you want to retrieve some of the samples, you have to take the tubes up the carousel, take the one that you want to use, and put it on an empty rack. So reversing the process of sample receipt. So what's important about this is, here it says in as little as 15 seconds, is that it scales very well, meaning you can have hundreds of thousands of tubes, and if in your next batch you want to use exactly 96 of those hundreds of thousands, then you just give the list to the machine, and the machine will tell you, here they are, here's the rack of the tubes that you want. If you want to do this manually, first of all, you'll have to have several freezers to store the same amount of tubes, and you're going to have to spend several hours, if not days of work, accessing the tubes manually one by one. So these type of machines are one way in which one can scale the building of a lab for diagnostics NGS. So in the next slide, we're gonna record these tubes, and here I show one type of software of this type. that will do this recording for you. Essentially, no matter how you start with, you're going to have a table of the records, and these records can be from the clinic that's supplying them or from somewhere else. And software like this can then ingest that table and then import it into the system in bulk. And you can do this via the website in this case, or also most of the systems have a programmatic API, meaning you can feed them via an automated process, command line process, for example. So now not only you have received the physical tubes and you've recorded their entries, including metadata associated to them, into an informatics system, you have the tubes ready, and you have a method to now generate batches of these tubes and do something with them. And so the first step is to extract the DNA from them. And let's say you've generated a batch here that is balanced by the different factors you want to account for: age, gender, provider, clinical position, etc. You can now take each of these batches and extract the DNA from the plasma into another tube that will contain the cfDNA. This is an example for cfDNA. It could be for something else. And so machines like the one that's shown here in the video will allow you to feed the machine with the plasma tubes. Importantly, some machines do it via this long strip. Some can do it via the rack themselves that you can take out of the freezer. And if they have bottom to the barcodes, then you can barcode scan everything underneath and keep track of what samples are being processed. For plasma, important consideration for plasma is that you get rid of the stuff that you don't want. And here it's a case of blood, but for plasma, there are considerations around fibrinogen and things that will affect your cfDNA extraction that are important. And also you don't want to extract gDNA, contaminant gDNA from the remaining cells. Here's an example of the scanning of the bottom barcodes. And so then it's placed into the next step to do something with them. And you'll obtain at the end of this another set of tubes or a plate that contains, presumably in a lower volume, the cfDNA that you wanted to extract. All these machines are complicated and need calibration. And so as part of the service of buying the machine, you'll have someone from the company programming the machine to do it exactly in the way that you've requested, with all the heads and all the tubes calibrated so that they do it correctly every time. And so at the end of it, starting from a rack of plasma tubes, you'll end up either with a plate or with another rack of tubes that contain the transparent liquid of your cfDNA extraction. In the next process, then, you may put these tubes back in the freezer and do another sample allocation, or you can chuck them into the next step, which would be the NGS Library Prep. If this is for cfDNA, you'll have a bunch of double-stranded DNA molecules, and you need to add sequencing adapters. Let's assume this is Illumina sequencing. You need to add the Illumina sequencing adapters so that your different samples, 96 samples, will get different UDIs so that you can do a multiplex run for all of them. And so here you are going to be using a machine that deals better with smaller volumes because the volumes of each of the samples that are processed through the library adaptation are going to be much smaller. There are different library preps for different applications. For example, the ones that don't do any PCR, just simply PCR free, they just add the adapters and pull them, or other ones that do PCR amplifications at different steps. Most of these machines have a very nice ratio of hands-on time versus total assay time, in the sense that even if they take several hours or over a day to run, what's important for scalability of the process is that they work all the time, but also that they have a relatively low hands-on time requirement, right? And another important consideration, which you saw in the paper, is that they can integrate the quantification of the DNA, meaning once you've library prepped the DNA, that you can quantify how much you have of it in each of the 96 samples. And so you can do the pooling at the end to have equi-represented samples in your pool for sequencing. Most of these steps, if not all of them, will be on barcoded materials, tubes and racks and plates, so that the machine can automatically barcode everything. And same for the reagents, so that you can keep track of which reagent lots you've used. The next step is to then do the sequencing. And for a high throughput facility, you want to use a high throughput NGS machine. Illumina released the NovaSeq a couple of years ago, and it's currently the highest throughput machine from offered from Illumina themselves. There is a roughly equivalent one from MGI BGI, the T7, with similar specs to Illumina, slightly quicker at the sequencing part. It's mostly being deployed as we speak in 2019 in China, and it hasn't gone out of China yet. So Illumina for short-read sequencing is the de facto standard, takes most of the market share, and allows them to hire people that are so good at explaining how to do the sequencing in their lab coats. And for non-Illumina technologies, the alternatives today are probably Oxford Nanopore in their GridION, PromethION, the highest throughput of the offerings that they have, and PacBio with their recently released Sequel 2 with the 8 million chip flow cell. But for Illumina NovaSeq, then you'll have a method that is relatively simple nowadays compared to what it was 5-10 years ago, of taking the pool of samples that you had from the library NGS preparation, feeding the machine with all the cartridges needed, and starting the sequencing run. Importantly, you will also connect it to your Basis account in the cloud. Here they're showing the different cartridges, and I think the video shows later on how to pipette your sample into the flow cells. So here is putting the cartridges in. It's really not that much more difficult than putting up the dishwasher if you have a dishwasher at home. The flow cell, very large flow cell for the very highest throughput method available. The machine itself can take 2 flow cells, and the runs can be started at separate times, which is convenient for labs that want to do this as the samples arrive. There's always going to be some batching, but it's good that you can submit 2 sequencing runs at 2 different times with this machine. The Oxford Nanopore GridION and PromethION also does this. Is a very good feature to have moving forward. The GridION with 5 different flow cells, the PromethION with 24 or 48 different flow cells that can be fed into the system at different times. So you can do a buffering, a much smaller buffering of samples into sequencing. And remember, all this needs some library prep from the previous slide, so you have to account for that as well. The NovaSeq being so high throughput, you'll want to multiplex your samples in, and so Illumina themselves, they offer 24, 48 of up to 96 multiplexing option, so you can put 96 samples. If you had a batch of 96 from the previous step, you can put it directly in one of the flow cells. If you require more sequencing, you can split your pool into more than one flow cell. If you require less sequencing, you can put it into the different lanes individually for the 4 lanes of the S4 NovaSeq flow cell, or the other lanes in the other smaller flow cells for NovaSeq. So once you've set out the sequencing run, it'll show you how it's going, and it'll have these flashy lights here showing progress. If it turns red, it's a bad sign. In your Illumina account, then you'll have something showing up like this, which basically shows that in this case, your run has completed. You see the cycle intensities with the indexes in the middle. In this case, they've done 2 by 150 cycle run. And then once you see your FASTQ generation completed, it means the data has been streamed into the cloud, or you can do it locally if you want, although I wouldn't recommend people bothering with it. Just do it on the cloud. And then you'll have the FASTQ files on your BaseSpace account on the cloud. The BaseSpace account has a command line interface and an API, and so you can access programmatically the FASTQ files that come out of your sequencing run so that you can automate the process end to end. And so in this process, you will have taken the pool and gone through the next step. Illumina also allows you to run pre-configured bioinformatics workflows and then do correlations of your multi-sample analysis to reference data sets. I'm going to talk about the primary and secondary tertiary analysis of bioinformatics in the next slides, and I'm not going to talk about it in the context of BaseSpace, but BaseSpace is an option. For other companies like Oxford Nanopore, they also have the Epi2Me offering, which basically connects the sequencing to the next step, has specialized apps and workflows to run things automatically after sequencing. And so in this video, it basically shows the process end to end. Here it's explaining a little bit how to set up some of these bioinformatic apps. In this process, it shows you the end-to-end process of feeding the machine with the cartridges, loading the sample into the little well that it's marked, put the sample here, and then submit the sequencing run for either one or both flow cells at the same time. Stream the data on the cloud, get the FASTQ files automatically on BaseSpace. So now you've got a bunch of FASTQ files. This is where the fun happens. I'm going to show you one of the platform's offerings to do this, which is DNAnexus, which has a web interface, but importantly also have a very nice command line interface and API, Python API or other types of API, and then you can generate, design and implement all your bioinformatics workflows and then submit them in batches programmatically. So in this graphical way, it will show us how to create a workflow by clicking on the new workflow tab. And a workflow is a collection of apps where an app will generate an input and output, and the output of an app can be connected to the input of the next app, so that one after the other, they will run and wait for the output of one step to kick off a cloud instance and run the next step of the next app. The system itself has a bunch of pre-configured both workflows and a bunch of pre-installed, pre-built apps that you can use. So if your system, if your analysis downstream of sequencing is something that can be composed of existing apps into the system, you don't even need to know how to create bioinformatics apps. You just click and add them here and drag and drop the boxes around so that they do what you require. And so I think they're going to show here how to connect an app to the next. Here they're doing some read mapping with BWMM. And then let's see if you now have different apps. And so left to right here, it's left-hand side inputs, and the orange boxes are the ones that you need to feed in your reads or other input files. And the right-hand side is the output. And what's going to be happening in the middle is you're going to be running an app with a specific parameters. And then you can click and drag some of these boxes from here down to the left-hand side of another app to connect them together. Let's see if that's what they show. So they're doing some FASTQ of the FASTQ files, and then doing some alignment, and then doing something else after the alignment. And here's how you click and drag. So you can see how clicking and dragging and dropping the app into the other side can connect the different apps together. So you can do it left to left if the FASTQ files need to be used in more than one place, or right to left if the output of an app needs to connect to the next one. And presumably that's what's going to happen now. They're going to connect the output of BWMM into the Bayesian caller. Yeah, there you are. So once you have this workflow defined, it comes out as a JSON object that you can interrogate and query, and then you can call it as many times as you have samples from your multiplex sequencing run from the previous step. The next step after that, once you've generated all this data, and this could be something like read counts or variant, etc., then you can do your multi-sample analysis. And so here I'm going to just show a couple of videos from Google that show how your machine learning that you want to do in your multi-sample analysis has been heavily simplified these days to allow people to do things that were quite complex in the infrastructure needed before. Google is very good at all things image-related videos and speech recognition, because that's where the company itself comes from. But at the same time, a lot of this can be applied to input files or input from different samples that looks a lot more like bioinformatics, right? And in this slide deck, we're going to assume that you just need to build a classifier. So we're going to fit the system with a bunch of samples that we know what they are, that are of known state, splitting them into training and validation. And the training is going to train as a classifier that then we can have in the Google Cloud system ready to make predictions, right? And so they show here in a graphical model, in a graphical way, how they build a model for how they click train for these image recognition system, and they get their ROC curves, and then they can predict based on an input. And in this case, the input is an image, but it basically gives you a prediction with a score. So this that we've shown here as an example in this video for classifying pictures of clouds in the classifier that you've trained, it's not that at all different from doing the same with bioinformatics, with genomics data. That could be variants, or it could be read counts in different genes from RNA-seq, etc. And so Google has been working hard in making sure the infrastructure underlying this work is as simple as possible for people to concentrate on what they know, the biology that they know. And so at the end of this, you'll have a diagnostics NGS lab ready to go. So what's the catch in all this? How come it's so simple as to have like a 10, 20 minutes explanation how to build a diagnostics lab? Well, the catch is that you need people that are trained in doing all these operations. And you also need money. You need money to be able to buy all the equipment and to run the experiments. I have here an estimate of how much money each of the machines costs, and it's in log scale so that it doesn't look very ugly. The ugliest part here is the sequencer. So if you buy an Illumina sequencer, you're going to have to, a NovaSeq sequencer, you're going to have to pay close to $1 million. There's going to be service charges every year, and on top of that, you're going to have to use buy reagents to use in each of your sequencing runs. Other offerings from PacBio, maybe $500,000 or so. Other offerings from Oxford Nanopore, much cheaper, to the point where the machine comes for free if you buy enough flow cells, enough reagents to do enough runs. And so these new players coming into the fore of NGS are opening up new avenues for people wanting to set up labs with a lower capex, because the capex of this sequencer plus a couple of liquid handlers for cfDNA extraction, library prep, it will already put you in the $1.5 million. The freezer, the vending machine freezer, can be another $200,000. Everything else, the software for freezer management, primary analysis, multisample, it's not really that CapEx heavy. And this is intentional in the sense that I've designed this slide deck to use the cloud for everything. So the freezer management software can be a cloud offering, and you can pay, say, $150 a month to use. The bioinformatics primary analysis can be straight pay as you go. You pay exactly for the number of seconds that you use the cloud instances and for every byte that you store into storage. And the multisample machine learning is exactly the same. You run X number of models and you pay for exactly what you use. So what's CapEx intensive here is the lab equipment, the liquid handlers, the sequencer, and the freezers. And all the collaterals of everything else, it's probably none of them will probably, including quantification of DNA, etc., none of them will probably make a 6-digit mark. Everything else will be lower than that. So assuming a $2 million capex to set up the lab, then you'll need about $500,000 to process 1,000 or 2,000 samples. Most of the cost will go into the DNA sequencing part and NGS sequencing, although the prices of sequencing are dropping. And so this $500,000, a bigger proportion of it will be non-NGS related as we go on in the future, right? Right, so this is how you set up a diagnostics NGS lab to do high throughput samples. You can do 100 samples a day or more. And it's that simple. I mean, it's not that simple in the sense that the catch is you need a good amount of money. You need to manage your people well, and you need to keep the machines running. And so I hope that you got a flavor of what's involved. And if you want to continue finding out more about the OmicsCast episodes, you can follow me on Twitter, twitter.com/Alberto Vilella. I'm happy to answer any questions you have on LinkedIn. And this slide deck containing the YouTube videos is available upon request. Until the next episode, goodbye.